Namaskaram. In last session, we have seen the double integration in a rectangular region. In this session, we will discuss how to evaluate our double integration in a non-rectangular regions. Okay. These are the solutions of previous homework. Okay. Consider a problem. Evaluate 0 to 1 minus x to x square y square x dy dx. So first we have to integrate the first integration. This integration means we have to integrate y square x with respect to y by treating x as a constant. Okay. So what is the integration of y square x with respect to y? Okay, so this become y cube by 3 into x minus x to x square. When y become x square, this become x raised to 6 into x by 3 minus, when y equal to minus x, this is minus of x cube. This is minus x cube into x by 3. So this is x raised to 7 by 3 and this is plus x raised to 4 by 3. Okay. So next we have to integrate this expression with respect to x. So this become, this is x raised to 8 by 8. So this become 24 and x raised to 5 by 5. So 3 is there. So it is 15, 0 to 1. When x equal to 1, this is 1 by 24 plus 1 by 15 minus when x equal to 0, this term becomes 0. Okay. Upon simplification, this becomes 13 by 120. Clear? Okay, so answer is 13 by 120. Next, we are going to interpret the limits, or what is the region of integration. Okay, next we are going to plot the region of integration from these limits. Okay, so here this is the range of y. Y is equal to minus x to y is equal to x square, and this is the range of x. X is varying from 0 to x is varying from 0 to 1. Okay. So actually what is y is equal to minus x? We know that y is equal to minus x is a straight line like this. And what about y is equal to x square? Yes, it is a parabola like this. Okay, y is equal to x square is a parabola. 1 second. Yes. So this is y is equal to x square and this is y is equal to minus x. And it is given that our variable y is varying from this point to this point. Clear? Y is varying from minus x to x square. So you can think a strip like this for notating the variation of y. So it is clear that y is varying from always minus x to x square. Clear? And what about the range of x? X is varying from 0. Suppose this is our 1. Suppose this is our 1. X is varying from 0 to 1. That means this strip is starting from here and moving like this. Clear? Moving like this up to this line segment. That means our region of integration is nothing. Our region of integration is this one. Clear? This is our R. Because this range of y and x together covers a region like a triangular shape. Almost like a triangular shape. This is a part of our parabola. Clear? So this is the idea of integrating non-rectangular regions. So if a region is non-rectangular, then we have to choose carefully the range of x and range of y such a way that together it covers the entire region. Okay. So in this session we will discuss mainly two type of regions. A type 1 region and type 2 region. A type 1 region means a region bounded on the left and right by vertical lines x equal to a and x equal to b. This is x equal to a and this is x equal to b. So these two sides are bounded by two straight lines and its lower part and upper part is bounded by curves. Okay. So and we assume that g1 of x is less than or equal to g2. Okay, that means a region like this. So in this region we can easily suppose that our region is like this. Then we can easily set up the integral. How? Suppose we have some function of xy and what about the order of integration? First we consider a strip like this. Okay, that means this is the variation of y. So here y is varying from g1 of x to g2 of x. Clear? And y is varying from g1 of x to g2 of x. And what about the range of x? To cover this entire region, the strip must be moved from this point to this point. That means x is moving from a to b. So a to b. And what is the order of integration? First we have to integrate with respect to y, because here y is the variable. So dy dx. So if it is a type 1 region, then we can set up the integration is like this. Okay, clear? If the region is type 1 region, then R is a type 1 region, then double integral over R fxy dA is equal to integral a to b integral g1 of x to g2 of x fxy dy dx. Okay, so first we cover y from g1 to g2, that means like this. Then our aim is to cover this entire region, that's all. Okay, to cover this entire region, strip must be moved from starting from this point to this point. That means x is varying from a to b. And we have one more type region, that is type 2 region. Okay, this is our type 2 region. In the case of type 2 region, the lower portion and upper portion both are bounded by lines. This is y is equal to c, this is y is equal to d, and this is y is equal to c. Clear? And left and right side is bounded by curves. The curves of the form x equal to h1 of y and here x equal to h2 of y. So how to set up the integral? Okay, our aim is to cover this region. To cover this region, first we have to consider the strip like this. Clear? Horizontally. So in this strip, x is always starting from h1 to the ending point is h2 of y. So that means h1 of y to h2 of y. So this is with respect to x, because this is the change of x, and our aim is to cover this region. This blue shaded region is our R. So to cover this entire region, y should varying from c to d, then only this strip cover this region. Clear? So c to d, and this is dy. Okay, so this is the idea of setup a double integration for a type 2 region. Okay, this is our type 2 region. Then far is a type 2 region. Then double integral over R fxy dA is equal to integral c to d integral h1 of y to h2 of y fxy dx dy. That means first we consider strip like this, then move the strip along this direction, y direction, to cover this region. That's all. Consider problem. Evaluate double integral over R xy dA over the region R enclosed between y is equal to x by 2, y is equal to square root of x equal to 2, and x equal to 4. Okay, so first we have to draw the diagram. Okay, first we consider y is equal to x by 2. We know that y is equal to x by 2 is a straight line like this. Okay, next we have to plot y is equal to square root of x. What is y is equal to square root of x? If you square this term, it is clear that it is y square equal to x. And what is y square equal to x? Yes, y square equal to x is a parabola like this. Okay, open to x-axis. And but it is clear that our y value is equal to positive square root of x. So y is always positive. So y is equal to square root of x is a part of this parabola such that y is positive. So which part? So this portion of the parabola. Clear? This portion of the parabola. So actually entire parabola is like this, that is y square equal to x. But we have a restriction, y should be positive. Y is equal to positive square root of x. So this portion of the parabola. Clear? Then suppose this is our x equal to 2. This is x equal to 2. Then that is a straight line like this. And we have one more thing, x equal to 4. Before plotting x equal to 4, we have to solve this point. What about the coordinate of this point? Okay, to find this point, we have to solve these two curves. So we substitute y is equal to square root of 2 in this equation and solve. So this becomes square root of x is equal to x by 2. Simply square it. So x equal to x square by 4. Cross multiply and to take the term to right side. So x square minus 4x equal to 0. X into x minus 4 equal to 0. Either x equal to 0 or x equal to 4. So this point is x equal to 0. So it is clear that this point is x equal to 4. And what is the corresponding y value? You can simply substitute x equal to 4 in any of this equation. If you substitute x equal to 4 in this equation, this gives y is equal to 4 by 2, that is 2. So the coordinate of this point is 4, 2. Clear? So this is our line x equal to 2. Now the region of integration is clear. The region of integration is clear. The region bounded by this straight line, the portion of the parabola, x equal to 2, x equal to minus 4. It is clear that this is our region of integration. Clear? So this is our R. So we have to integrate over this R. Is it type 1 or type 2 region? Yes, it is clear that it is type 1 region. Or our aim is to integrate over this small blue region R, that's all. Okay, so to cover region, better you consider vertical strip, right? So vertical strip means here the changing variable is y. So what is the value of y from the straight line? It is x by 2. Clear? And what is the value of y on this curve? That is y is equal to root x. Clear? So the first integration is with respect to y. It is varying from x by 2 to root x. Clear? Our aim is to cover this region R, this blue region R. To cover this region R, the vertical strip should move from this point to this point. That means x is varying from 2 to 4. So this is the setup of this non-rectangular region area. Non-rectangular region. Okay. And the first is with respect to y. So dy dx. So to evaluate this integral, we have to perform this iterative integration. Okay. Okay, now it's only a matter of integration. That part is very easy. The main portion of these type of problems is the setup of this iterative integration from given data. Okay, then first you have to perform this integration. Okay, this become xy square by 2, and this is the limits. When we substitute upper limit and lower limit and simplify, then equation is like this. Next you have to integrate with respect to x. Okay, so this integration is a integral of x square is x cube by 3. That's why this x cube by 6 minus this x raised to 4 by 4. Already 8 is there. That's why it's 32. You can substitute upper limit and lower limit and simplify. This become 11 by 6. Okay. Yes, 11 by 6. Next problem. Evaluate double integral over R to x minus y square dA over the triangular region R enclosed between the lines y is equal to minus x plus 1, y is equal to x plus 1, and y is equal to 3. Okay, so first we have to draw these straight lines. How to plot y is equal to minus x plus 1? This is our x value, this is our y value. When x equal to 0, y equal to 1. When y equal to 0, what about x? X equal to 1. Okay, so this straight line is passing through 0, 1. Suppose this is our 0, 1. And this point is 1, 0. So this is a straight line passing through these 2 points. We know that there is a unique straight line. So this is nothing, y is equal to minus x plus 1. Similarly, you can plot the second straight line. Okay, this is the equation of straight line, and when x equal to 0, y equal to 1. When y equal to 0, x equal to minus 1. That means the straight line passing through 0, 1 and minus 1, 0. This is a unique straight line. And we have one more equation, that is y is equal to 3. So this point is 1. So y equal to 3 is somewhere here. Okay. So region bounded by these 3 straight lines. It's clear that this is our region R. This triangular region is our R. Okay. We have to integrate over this region. To cover this blue shaded region, better you consider a strip like this horizontally. Horizontally means the changing variable is x. So what is the lower value of x? That is from this equation. In this equation, y is equal to minus x plus 1. So what is x? X is nothing, 1 minus y. So the lower value of x is 1 minus y. And up to this point. This point means here, this is the equation of the straight line, y is equal to x plus 1. So what is the value of x at this point? That is x equal to y minus 1. So 1 minus y to y minus 1. This is the range of x from this point to this point. To cover this region, we have to start this strip from this point to move in the y direction up to this point. Okay, that means y should vary from 1 to 3. So this is the change of y. So first we integrate with respect to x, because this is in horizontal direction, then dy. This is the setup of this integral. Next we have to compute this iterative integral. So this is x square minus y square x and 1 minus y to y minus 1. Substituting x by y minus 1 term is like this. Minus the lower limit is 1 minus y. And you can simplify this expression by first you square these two terms and simplify. So upon simplification, this expression is like this: 2y square minus 2y cube. Then you can integrate this with respect to y. So this become, so this is 2y cube by 3 minus 2y raised to 4 by 4, 1 to 3. You can substitute upper limit and lower limit and simplify. This become minus 68 by 3. Okay. Yes, minus 68 by 3. And one more thing, now we solve this problem by identifying this region as a type 2 region. You can also solve this problem as identifying this as a type 1 region. That means you consider first we consider a vertical strip. So what about this integral? Integral become double integral, and what is the change of y? Here y is varying from minus x plus 1 to, what is the upper value of y? Here y is always 3. Clear? And the function, and here this dy dx. The problem is, if x is what is the lower value of x? X is minus 3, x is varying from, sorry, minus 2. If x is varying from minus 2 to up to 2, right? But after x equal to 0, what about the lower value of the strip? The lower value of the strip is from this straight line. You got it? So this is different from minus x plus 1. Here its value is x plus 1. So we can solve this problem as type 1 region by identifying these are two separate regions, R1 and R2. Then this integration is equal to minus 2 to up to 0. Okay, you can integrate, this is up to 0 plus next integral. In this integral, our y value starting from x plus 1 to 3, and what is the range of x? X is varying from 0 to up to 2. Clear? Dy dx. So if you identify this problem as a type 1 region, then this integration as a sum of these two. Okay, it is more complicated than a previous case. So better you solve this problem as a type 2 region. You got it? Anyway, you got the same answer. If you consider these two integral and take the sum, give the same answer, minus 68/3. Okay, next problem. Find the volume of the tetrahedron bounded by the coordinate planes, and the plane z is equal to 4 minus 4x minus 2y. So first you have to draw the rough picture of this region. Okay, what is the intersection points of this plane with these axes? The intersection with the z-axis means we simply substitute x and y 0. So z equal to 4. So it is passing through this point. When x and next you have to find the intersection with the x-axis. So you substitute y and z equal to 0. When y and z equal to 0, this will become 4 minus 4x equal to 0. That means x equal to 1. So passing through this point. And one more thing, next you have to find the intersection with the y-axis. So put x equal to 0 and z equal to 0. So this becomes, so 0 equal to 4 minus 2y. So 4 equal to 2y. So y is equal to 2. So it is passing through this point. So it is clear that this plane is passing through these 3 points. So that is gives a rough picture of the our region. Okay, a plane is a slanted plane like this. So we have to find the volume of this tetrahedron bounded by coordinate planes and this plane. Clear? To find the volume, we have to integrate our function. Our function is 4 minus 4x minus 2y over the region R, this triangular region. Okay, so to find the triangular region, it is clear that this side is bounded by x-axis, this is by y-axis, and this is by a straight line. How to find the equation of the straight line? This equation of straight line is a part of this plane when z equal to 0. So you simply substitute z equal to 0 in this equation of the plane. That gives the intersection of the plane together with xy plane. Clear? So what is the equation of the straight line? Okay, so when z equal to 0, this become like this, and y is equal to 2 minus 2x. So equation of the straight line is y is equal to 2 minus 2x. Clear? So next we have to integrate all this triangular region. Either we can treat it as a type 1 or type 2, whatever be no problem. So I'm going to consider a strip like this. First we consider a vertical strip. Here what is the lower value of y? Here the lower value of y is 0. And what is the upper value of y? Y is from the straight line, that is y is equal to 2 minus 2x. Clear? And to cover this region, x should vary from this point to this point. Then only this strip covers this entire triangular region. So x is varying from 0 to 1. Okay, so it is easy to set up the integration. Okay, we know volume is equal to double integral, and we can evaluate this double integration over this triangular region, and y is varying from 0 to 2 minus 2x, and to cover this triangular region, x is varying from 0 to 1, and this is dy dx. Okay, this triangular region is same as this triangular region. We just rotate 90 degree. That's all. Okay. So y-axis is here and x-axis is here. That's all. So that's the idea. So next you have to perform this integration. So this is equal to 4y minus 4xy minus 2y square by 2. So that become y square. And you can substitute lower limit and upper limit. So simplify. So this become 4 minus 8x plus 4x square. Then you integrate with respect to x. So this is 4x minus 8 into x square by 2 plus 4 into x cube by 3. And limit is 0 to 1. Upon substituting upper limit and lower limit and simplify, this become 4 by 3. Okay, so this is the final answer. Okay, this is your homework. Thank you.